usage of artificial intelligence in the production technology, I see there are lot many of carefully thought topics on this area. That said, let me quickly, as Dr. Srinivas already mentioned, right now the biggest program that we are spearheading is the TQNC 60i quantum computer, which is a hybrid quantum computer. So in this next 40 or 45 odd minutes, the way I wanted to present is to give an overview of quantum computing, just so that because in the audience there might be many people, many experts who already know a lot of quantum computing, about quantum computing. There may be some of the audience who are just getting onboarded into the quantum computing paradigm, and there might be someone with mixed skill set. So just to bring everyone into the same platform, I wanted to initially give an overview of what quantum computing is, then naturally, gradually heading into the role of mechanical engineering within this quantum computing system. More specifically, neutral atom and trapped ion system, where we are closely working. So hope that is fine. Before I start, let me check if there are any further expectations or any questions so far, please. Perfect. Perfect. Thank you very much, sir. So that said, hope you can see my slide, which now says why quantum computing is required. So you must be hearing this word quite often these days on quantum computing. There's a national quantum mission, which is providing grants, providing a lot of network and support to quantum ecosystem in India. But we'll take a step back and try to understand why even a quantum computing is required. So don't we, the classical computing as we do it, the mobile phones, the laptops, all of the things that we are, electronic gadgets that we are using, are they not good enough? Is a natural question. Probably that is a very good point to start with. So as you know, the Moore's law has been slowly reducing, and classical computers are hitting the fundamental limits of what is possible in computing, right? And classical computing uses bits and bytes, and entire our technology stack is predominantly based on this fundamental basic building blocks. That said, there are increasingly harder problems which are emerging, which are getting difficult for traditional classical computers to solve. And precisely why quantum computers are emerging as as a next generation of technology, where you will be able to solve very hard questions which are difficult to solve by classical computers. That said, they are clearly not the replacement for classical computers. There most likely will not be a case where all the classical computers that we use will be replaced by quantum computers. No, it is a more of a case of coexistence, where both will exist and quantum computers will solve those difficult hard problems which are difficult to solve by classical computers. In the coming slides, we are going to discuss about what are the industries and use cases that these quantum computers solve. And let's go one step deeper. What exactly is quantum within a quantum computing? So for that, we'll have to go a little bit back into our high school physics and engineering physics and chemistry, where we get into the orbital and energy levels of various fundamental building blocks of nature, which are electrons, protons, and neutrons. As you know, it has been established in science that the energy is quantized between various energy levels within an atom. So utilizing these energy levels to solve a class of problems is where fundamentally the origin of quantum is coming from, as some of you might be already aware. And predominantly, there are three fundamental principles which are of great importance, which is superposition, entanglement, and interference. These will be the fundamental blocks of where quantum's supreme energy is coming from. It's the entire special capability to solve hard problems is emanating from these three fundamental areas. But there are so many other things, but I'm just trying to simplify to make it easier for consuming. So that said, using these superposition, entanglement, and interference capabilities, quantum computing is able to do certain class of problems in extraordinary exponential speed. Something which used to take years and decades could potentially be solved in hours and in some cases minutes. So that gives phenomenal advantage over classical computing. So before further delving deep into what is quantum computing, let us take some very normal experiences just to get an analogy of intuitive understanding of quantum computing. Imagine a leaf, the mother nature, which is there working always, all throughout, is a primary example of quantum computing or quantum principles to happening all the days. Now we are trying to do is to simulate or biomimic the capabilities of Mother Nature out there. As you can see, one of the tagline of our company is the nature is quantum, the TriQuanta Labs one. So we are greatly inspired by nature in solving the quantum computing problems. That said, in a leaf, you would remember in the photosynthesis activity, the photons reach the surface of the leaf and then eventually go into chlorophyll generating sites, and that's where the entire photosynthesis happen. But the point of touching of the surface to the chlorophyll site, there are thousands and millions of alternative paths for the photon to traverse. But however, Mother Nature is extremely smart. It deploys the quantum computing in action. It is able to find the shortest path for the photon to traverse while evaluating million other parameters and then identifying the shortest path to go into the for the photon to travel from the surface to the chlorophyll site. That said, you can understand with this example, you can understand what is the heart of quantum computing. It is a case wherein hundreds of millions of alternative paths are there, but still you have to identify one shortest path. That is when quantum computing comes into its ultimate power, largely derived from the mimicking what nature is already doing. Another prime example of quantum computing in action that Mother Nature does is the capability of cryptochrome vision that birds have. Birds have a cryptochrome ribosomes and specific molecules hidden inside their eyes, which this is an established science, and there are papers to back it up, wherein it will able to entangle their position with the Earth's magnetic field, using which it will be able to traverse to maintain this entangled position. They'll be able to orient, and then they have the vision and idea of navigation without any compasses and global positioning systems. So this is the power of Mother Nature using quantum computing principles in its regular life. And incidentally, you will find that just day before yesterday, NQM second round results have come. At least 3 or 4 startups have been funded, provided with grants, which are in the area of quantum sensing. So the entire quantum sensing, which is a parallel topic to quantum computing, derives its power from this similar phenomena. So the point I'm trying to drive home, and which we are greatly appreciative about, is that quantum is at work. It's there 24/7 round the clock. Just that now we are bringing those paradigms into computing for solving specific class of problems. With that said, let us jump into what are the fundamental building blocks of quantum computing. As we discussed, for classical computing, we use bits and bytes. But for quantum computing, we use something called qubits. Qubit standing, you can say it is quantum bits. So unlike, classical bits are 0 and 1, right? So other day I was explaining in one of the seminar in NASCOM to explain how do you explain a qubit. Now imagine taking a coin in your hand, right? And this coin, when you flip into the air, can anyone of you attempt and tell whether it is heads or tails? As you can guess, when it is flipping in the air, it is in fact a superposition of both. It's a mix of heads and tails, both continuously changing. But when do you know finally whether it is going to be heads or tails? When you put it in your hand and close it. So then you will see whether it is heads or tails. So this simple analogy is a very rudimentary example of largely, I mean, we can make it extremely complex using vectors, and you can use Hamiltonians and do very complex stuff. But essentially, when you get to the simple analogy, this is what it is in action. Here, the state of heads or tails is in a continuous superposition until you measure it. So exactly same thing happens in quantum computing. So there is a state of superposition when a problem or challenge is mixed, and you use gates called quantum gates. There are many gates like C0, Hadamard gate, and there's a class of gates which will work with these qubits and process the information. And eventually, after everything is done, eventually you measure it. It is like holding the final coin after it is flipped. So this measurement collapses the quantum state to give the final answer of any class of problems. So this is how a fundamental quantum computing paradigm works. In a short time, I mean, there are courses which runs into days and years to explain these topics. And National Quantum Mission and AP government, they have created a whole range of quantum computing programs and training programs where this phenomena is explained in greater detail, but I'm trying to keep it relevant so that we address our subsequent slides, which are specifically pointed towards mechanical engineering. So as I said, the classical bit is 0 or 1, but a qubit is represented by this bracket notation as it called, largely attributed to phenomenal Dirac, the scientist who shared his work along with Schrodinger, whose famous Schrodinger's equation is one of the fundamental element in the quantum mechanics. So Dirac's notation is called Ket0 or Bra0, Ket0, bracket notation as they call it. As you can see, alpha Ket 0, beta Ket 1 is a superposition of two qubits, which is 0 and 1. So these qubits become the fundamentals of quantum computing. But now you may ask, theoretically, this is fine. How do you physically realize these qubits, right? In a semiconductor world, there are registers and clocks where you realize these flips and flops. But how do you realize these quantum states, which are not either 0 or 1, or rather it is an overlap of 0 or 1? How do you physically realize that is a natural question that you may have at this point. So precisely why this is of big importance, because this one particular third point, which is the electron spin, ion energy levels, neutral atom states, this one point differentiates whole entire quantum computing industries into 6 or 7 major modalities. So this is and hence I kept this point to make sure that once you understand why there is a qubit and how this qubit is eventually realized using multiple methods, you will be able to understand and appreciate the entire quantum computing industry. May it be IBM and Rigetti's and Google's superconducting systems, may it be TriQuanta's hybrid systems, which includes neutral atom and trapped ions, or IonQ's trapped ion system, QEra's quantum computing system, PsiQuantum's photonic systems. So all these are different class of quantum computers, but you need to understand why there are so many different types of quantum computers. That is because the way of physical realization of each qubit state is fundamentally different. And which is what, once you look at this, a third point will be appreciated. If you are assessing the ion, if you're taking ion energy levels, then you are essentially going into a trapped ion based of quantum computers. And there are many startups, including us, TriQuanta, which are utilizing ion energy levels. So is the case with the neutral atoms. We predominantly call it as Rydberg states, using a popular phenomena called Rydberg blockade, wherein atoms' size expands in a Rydberg state and becomes easy for optical tweezer to handle and process that qubit. Again, there's not going to you not be racking brain on what is these topics about. We are going to demystify all this in the next few slides for you. So I hope now you understood what is quantum computing, why it is required, and what is a fundamental block of qubit, and how this physical realization of each qubit is creating class of different types of quantum computers. In the next slide, before diving deep into each of the modalities, let us quickly see and size the opportunities that we have using quantum computing. If you can see on the slide, there are a whole bunch of industries which are going to benefit it by utilizing quantum computing in their business areas. In finance, portfolio optimization, I don't want to read out the slide, but essentially I wanted to provide that there are several industries which are getting benefited from quantum computing. And the size of the opportunity is also not trivial. It is not trivial. For in 2025, it was about $3.5 billion market size of the quantum computing, sensors, the whole range of technologies around quantum. And it is projected to be $20 billion in 2030. And but if you see, by 2035, it's expected to be 1 trillion. You can see the jump from 20.2 billion to 1 trillion USD in terms of long-term economic within a matter of 5 years. So that means something, right? So there is phenomenal opportunity which is going to unfold in front of us. Thankfully, thanks to this session and many such progressive thinking sessions, today we are able to be the first set of people who are going to not only understand, but write this wave of change using quantum computing. For India, what it means that it is a time that we build self-reliant quantum ecosystem. We need to have our own set of quantum computers. We need to have our own set of quantum sensors and all the materials specifically. Materials is a big topic of this FDP program. Sorry, is there a question? Okay, sure. So if you have a question, please feel free to stop. So for India, the opportunity for building a self-reliant quantum system ecosystem is very, very high. And which is what the government has already started. It is one of the first governments in India, in the world, to come out with a comprehensive quantum mission, which is called National Quantum Mission, which allocated $1 billion at that point of time, which is about 6,000 crores. And startups and academia are encouraged to work and develop the quantum technology. Maybe I think one of the participants may have to go on mute, I guess so, just for the benefit of others, please. So with that, let me jump into if you remember, we discussed about the physical realization piece here. There are various ways of realizing qubit. Based on the various ways of realizing qubits, you have what do you call as different types of quantum computing. Hope you can see my slide. On the left, I have listed what are the, these are not the only ones, but these are the most popular ones where promising and strong number of qubits have been already generated. May I request Vignesh Garu to go on mute just so that everyone gets better audio experience, please. Moving on. So here is I request you to look at this slide for a moment, because the subsequent part of the session is going to be is fundamentally dependent on this particular slide. So this superconducting system is one of the most popular system, and I will show you how a superconducting quantum computer is and how it works. But fag end at the right, I have listed something called mechanical engineering challenges. The point I'm trying to mention here is that however great and however popular the superconducting technology be here, there are roles for mechanical engineers. I think there is some audio noise. I hope it is not disturbing too much. It is from, I believe, Mr. Vignesh Ji. Okay, let me continue. So, as you can see, for each of the modality, there are mechanical engineering related challenges. And all of us here have a role to play in enabling and creating future set of talent, skill, and resources who can solve these problems. Once they are solving these problems, they are enabling the entire quantum computing ecosystem. And in R25, I had opportunity and privilege to be part of BOS, and with the team and with the support of amazing BOS members, we had opportunity to introduce some of these topics in the syllabus, and with the intention that once the mechanical engineering students, upcoming mechanical engineering students, have embracing and understand the importance of cryogenics and low vibrations, precision traps, and ultra high vacuum, all these topics, they are going to become a key asset, not just for India, to the global industry of quantum computing. With that intention, the R25 editions have been made thanks to the support of the board members. So with that, let me jump into the heart of the topic, which is the mechanical engineering role in quantum computing. And most of the times there's a misconception that quantum computing might be a topic of computer science department, or maybe electronics department, ECE, or at max triple E. I think this is a general perception I have had when I'm speaking to some of the academia and industry experts. But one of the principal top point that I wanted to drive home is that it is not the case. Mechanical engineering has a significant amount role, if not 50% of the role of quantum computing derives from mechanical engineering in enabling the quantum computing. So it could be, and again, see how beautifully this FDP has been designed. Each of the three core pillars, which is innovations in the materials, innovations in the manufacturing processes, and the intelligent systems in the in mechanical engineering. All these three again becomes and plays a vital role for mechanical engineering to enable the quantum computing, translating the quantum physics and mechanics into a scalable hardware. So with that, we will jump into the modalities and understand each of these quantum computing modalities in a little bit more deeper. I think this image is very popular. Anytime you hear a quantum computer, this is possibly something come to your mind. This, can any one of you take a guess where in this entire equipment that you see on the left, where exactly is the quantum computer? I'm opening the floor for quick responses, if you can. In this entire image, where is a quantum computer? Interestingly, the entire structure that you see it is not a quantum computer, and those who are already familiar with the superconducting system would know this. That actual quantum computing processor is right under the base plate, as they call it here. So the rest of the stuff is what popularly called as a dilution refrigerator. And this refrigeration is a heart of mechanical engineering. And first time when I realized it that, and when I spoke to some of the people in the industry, they said that while operating quantum computers of superconducting, 60 to 75% of their work is heat management. It's the thermal management to make sure that the base plate is to the order of 10 to 20 millikelvin, which you agree that is one of the it is one of the lowest temperature. It's possibly the closest to the absolute zero. So that is a temperature which is envisaged at the bottom of the base plate. So this entire structure is a multi-stage dilution refrigerator inside which you have cryostats, and there's a lot of multi-layer insulation and thermal anchoring involved. Phenomenal amount of vibration isolation and damping is done in the structure and the top of the quantum computer. And there's a superior focus and continuous innovation in terms of having ultra low thermal conductivity materials and wiring. And to monitor the entire system, there is a focus on AI and digital twins for thermal control. How do you ensure each plate at each level there is a temperature maintenance so that at the bottom of the base plate you have the required 10 to 20 millikelvin. So one of our strategic partner or acquaintance is Blue Force, which is one of the world leader in dilution refrigerators. So as you can see, this is a dilution refrigerator. And this image on the right side is from the QMAC lab in IIT Bombay, in Dr. Vijay Raghavan's lab, who is one of the pioneer in superconducting quantum computing in India, where a six qubit quantum computer is already there. This is as you can see, is a dilution refrigerator out there. There are cables which are specialized cables to ensure the entire cryogenic cooling happens. So the entire cryogenics and dependence on helium-3 and helium-4, and this makes one of the most important area where mechanical engineering plays a role. So before I move on to other modalities and role of mechanical engineering, maybe I'll pause for a moment to see if there are any questions, please.
Yeah, you mentioned the materials part also. Can you throw some more light on what materials of interest should be?
Sure, perfectly, sir. I think exactly the next topics will particularly highlight the role of materials there. So moving on, let me go back to this is our fundamental slide on which everything works. TriQuanta Labs works with these two technologies, trapped ion and neutral atom, and then forms a hybrid. We'll discuss that. So now we discussed about superconducting quantum computer. Now let's touch base about other principal modalities called trapped ion quantum computer. So in a trapped ion quantum computer, you use precision power traps, which are used to trap the ions. We use various ion species. People used calcium ions. At TriQuanta Labs, we use barium ions. And some of the players like IonQ, they use ytterbium. They were using ytterbium, now they are moving to barium for superior material characterization results. So there is electrode microfabrication which is involved. We need to be sensitive to the fact that we are talking about atoms and ion scale, which is smaller than the chips that you see in the computer, the traditional mobile phones, etc. They are mostly 2 nanometer chips and 3 nanometer chips. Now we are talking at a scale of atoms and ions, which are many degrees lower than the size of the traditional classical computers, which means the fabrication of equipments calls for innovations in the precision engineering, and I'll touch upon ultra high vacuum chambers. And this is where, as sir asked, there is a requirement for new materials which have better characteristics in terms of outgassing. So we know that in the scheme of high pressure or ultra high vacuum, outgassing is a phenomena that happens in the materials, and hence new alloys have been continuously been innovated to prevent this outgassing characteristics. And that's where we require a lot of material-led innovation to happen in enabling the quantum computers. So here, while we deep dive into that, I have listed here out those topics. ME stands for mechanical engineering. These are the areas where mechanical engineering plays role in each of these areas to make them happen. As you can see, without any single one point of which are mentioned here, it is very difficult for quantum computers based on these modalities to deliver any qubits. Even one doesn't work, you will not see any qubits, and quantum computing comes to a standstill. Same is the case with the superconducting. If this thermal noise or thermal is not maintained, you will not have any quantum computing
Sorry,
to
sir,
be
one
seen.
small question.
Please.
Are you preferring outgassing or you don't dislike the
We
outgassing?
don't we don't we don't like outgassing.
Oh yeah, materials are also same thing. Okay. In
Exactly.
vacuum system, it's going to disturb the pressure levels here.
Absolutely. So outgassing is should not happen. Thank you. So that is where. So hope by this time we are clear that our engineering has principal role to play in the entire enabling entire quantum computing. I also want to touch about photonics, which is a principal paradigm of say PsiQuantum and many other players. Microsoft incidentally uses topological conductivity. So this is one area where you talked about materials. Topological conductivity is predominantly where innovation in material sciences makes a lot of difference to topological states of those materials, and hence the quantum computing related to it. So Microsoft is heavily working in this paradigm, and photonics is followed by players like PsiQuantum, where again, to create the waveguides of handling photon level control, there's a phenomenal role the mechanical engineers needs to play, including the fiber alignment. With that, let us quickly get back into understanding the basics of neutral atom quantum computing. So the way I structure is we'll quickly study basic of neutral atom quantum computing and about trapped ion quantum computing. Only then we'll be able to understand what a hybrid is, which is what essentially we're building. So neutral atom quantum computing uses an atom as a qubit. To the right side, there's a visualization of how a particular atom is locked into a array, and it is tweaked using something called optical tweezers. So we use lasers for that to optically tweeze. So which means that we need lasers which have the line width which is equivalent to the size of an atom. So it runs into the frequency of the lasers runs into few kilohertz and in some cases hertz of frequency. So that is extremely thin line width of lasers which we use, using which we hold the atoms right in the center. If you can see, if you can follow my pointer, right in the center, there is a magnetic coil. In this is called MOT, magneto-optical trap. This magneto-optical trap is holding inside a vacuum chamber. It can be clearly seen in this particular schematic diagram, which is there here. So there is a vacuum chamber here, and then there is a laser going into it. Into this vacuum chamber, we introduce various atomic species, which are suitable for neutral atom quantum computing. People used calcium, potassium. At TriQuanta Labs, we use rubidium. This rubidium is introduced into vacuum chamber, and this vacuum chamber holds to the ultra. It is ultra high vacuum range. It goes into 10 power minus 11 torr for the to be able to reduce the thermal noise. Essentially, you might by this time you must have understood, right? It is about reducing the thermal or any other noise using various parameters. Superconducting quantum computing utilizes the thermal way of cooling it down. It goes to absolute zero. But neutral atom quantum computing, it works at the room temperature, but it plays around with the vacuum. So it uses ultra high vacuum and then uses a principle called laser cooling. Using laser cooling, it will locally cool the rubidium atoms, which are kind of held inside this MOT, as you call it. You can see the optical, all these are fiber coupled lasers which are going inside. And then this is a camera, the red one is a camera, which is the macroscope objective, which is also, in our case, we use EMCCDs, charge coupled device cameras, which will use the atom qubit, which will visualize the atoms which are held in the trap. Essentially, we are holding the atoms in a state. We are playing around with the energy levels of each atom by carefully using lasers for that. There are various frequencies of lasers that we have to use to, and that is where the core research of our team lies in. And globally, everyone works on the same phenomena, where you will be able to play with the D1, D2 kind of energy lines, and then calculate the fluorescence and realize a qubit from that. Essentially, you have a problem. There is a problem to be solved. It is to be mapped into qubit, as I call the circuit. This circuit is loaded into these qubits. After calculation out of here, it will be measured. Eventually, we'll be able to give a solution to the problem which is originally mapped into basis states. So this is a high level. As you can see, this is a neutral atom array, and this is onto the left. And we are playing with something called Rydberg state in the ground states. And then we are using whole bunch of arrays to play around with these atoms. If you go to Google right now and type in what is the largest qubit size which is demonstrated, which I encourage you to do as you listen to the session, you possibly will get the result of neutral atom quantum computing, where they have demonstrated 6,100 qubits, which is one of the largest demonstrated qubits. However, they are not entangled, which is a harder problem. But however, the point I wanted to mention is scalability. So neutral atom quantum computing brings in phenomenal scale, and beauty is that using optical tweezers, you can move one atom from one place to other place, effectively controlling their entangled states. In a superconducting quantum computer, it is a printed circuit. You have Josephson junctions, which are printed on the base plate in the QPU, and they're fixed. Once fixed, they are fixed. You cannot change. But however, in a neutral atom, you can play around with the atoms because they're in a free space in a MOT. Using lasers, you can play around with this. And hence it gives a, in once you get into the problem circuits, which is not the scope of today's session. Once probably we can have a different session for that, wherein at that stage this reconfigurability of atoms gives a phenomenal advantage over traditional superconducting quantum computing systems. And hence the strengths is the scalability and configurability of neutral atom quantum computing. However, again, I want to bring back to the original topic of role of mechanical engineering. You can see everything here is a precision engineering dependent. And in fact, I'll see if I have one of the component here, wherein in terms of protecting ultra high vacuum, you need to have micron level scratch free resistant surfaces. You need to manufacture that. And at the same time, you need to create systems like laser diodes, which are playing at this line width of an atom, which means precision engineering has a phenomenal role to play. Mechanical engineering has a role to play to be able to make quantum computing happen and scale. With that, we will jump into the basics of trapped ion quantum computing. Onto the left, what you can see is the trap, which is, I hope you can follow my pointer here. This is the trap. It is called, in a popular terminology, it is called quadrupole Paul trap, wherein you see there are different electrodes, and in between there are DC anode cathodes. There is a space in between. This small space is essentially the trap for ions. So atoms are controlled using optics, whereas ions, since they have a charge and they are slightly bigger, they are controlled with electronics, RF and DC electronics here. So the same trap here is what I'm showing here. That is where it is here. The ions are getting trapped here. They are observed with CCD. The glow here, each of the glowing bubble with various thermal spectrum within each dot is a qubit. Essentially, what here you are seeing is a 8-qubit system, right? And the levels of fluorescence will tell a lot about the overall qubit characterization. This is an image from another popular quantum computer. Again, this is again I'm showing before we reveal what we are building at the TriQuanta. But what you are essentially seeing is that inside an ultra high vacuum chamber, you are going to have this Paul trap, and this Paul trap is the initial version. It is only in 2D. But now we are working, the industry is working in building an array, which is you will have a 2D and eventually three-dimensional traps wherein you trap the ions. So it will, and hence, but the point is that all of this is happening in ultra high vacuum. Even if there is a degree of leakage or outgassing, your entire qubit state ability of a qubit to retain information for the duration, that coherence is lost, which means there's a leakage, you're gone. So the quantum computer doesn't work. So the benefits of Paul trap is that,
One small
yeah,
question.
sorry.
See, in the vacuum systems, generally, rotary mechanical pump, then we go to the diffusion pump. And there also the trapping of the molecules, atoms is done. But you're talking to 10 raised to minus 11, long way
Correct.
to go. Is it
Yes.
a similar thing you're talking about, the trap or power trap?
No, so what you said is right. With the turbo and rotary, we can easily go to 10 power minus 3 and minus 4. In some extremely good rotaries, we can go to 10 power minus 5. But however, beyond that, as you said, we'll be
Diffusion.
using diffusion pumps, and we also use ion pumps to reach 10
Okay.
power minus 11. Once you get to the ion pumps, they are essentially doing at ion level of removal and separation of particles from the vacuum chamber system. But however, the point is that pure pumps will not be able to deliver that. You need quality baking. So you need to have experts who knows how to bake it at a point to reach and sustain that 10 power minus 11. So with turbos without baking, while you can easily go to high vacuum, but beyond that, as you rightly gauged, you need diffusion and ion pumps, and not even just that, you need to do a lot of good baking, and that is what the teams need to specialize. You need to know how best and quickly to be able to bake it and keep it baked to ensure 10 power minus 11.
Thank you, sir.
Perfect. So as question is asked, that's perfect question. So the inside this, you need to maintain 10 power minus 11. So and hence you use a combination of rotary, diffusion, ion pumps, and then you go for baking, and that is what how it is. And that's where the ovens make a lot of difference. Mechanical engineers have huge role to design smart systems to be able to orchestrate the entire thing. So you need to measure and monitor the vacuum, and then also be able to bring in the baking systems to ensure that you reach 10 power minus 11. So that is where we are, and hopefully you got a glimpse of what trapped ion and neutral atoms are there. Now you put merge neutral atom and trapped ion together into a single system. That's where we have the TriQuanta hybrid quantum computing. So while each system, right, the neutral atom and trapped ion, they also have their own cons, right? Neutral atoms are highly scalable, but they have shorter coherence times. You can see that. So, but trapped ions might not be as scalable as neutral atoms, but they have extremely high coherence times. And now, what if you can bring both of them together in a single system, single UHV system? That is a heart, that is the genesis of TriQuanta, and where we are building this unified system in a single UHV system. So this is in our lab, and you see our teams who are expertised. They're working on various other systems uh, on related to trapped ion here. As I kind of zoom in, this is not atoms or ions. This is the dust which is done. But the point is, I just want to drive home the point of how the trapping happens. This is essentially dust which is got fluoresced by the green lasers. But however, we don't, with dust we can't do anything. But the concept is that once you stabilize there, the ions can be in that state for a very long time. That is the point I'm trying to tell. That gives a very long coherence time of trapped ion systems. And this is a rubidium MOT. We discussed about MOT. The fluorescence of rubidium is what you can see here, and which forms the, you initially you find a rubidium MOT cloud, and then you separate them into individual ions using specialized technologies. That is where the whole research and that's the whole work is going on. Initially, you will see the cloud of barium ions like this, and you will have to separate the ions of this cloud from each of them and separately position into separate area. Now you can see here about 11 ions in a line, and now each of them is a qubit. So this is a 11 qubit system. So to make a 11 qubit quantum processor, now you can imagine why we have chosen this system and why we are building. We're super excited about this. This 11 qubits can be easily expanded to 30 qubits and 100 qubits also. So it is all about the how precisely you are able to convert this cloud of ions into different arrays and then play around with each of these ions. So the scalability is phenomenal. So, and hence that gives us a phenomenal confidence that in the quantum computing world, we will be, by utilizing the benefits of both neutral atom and trapped ion together, we will be able to do a scale significantly well beyond 1000 qubits very soon.
Sir, one question, sir. This we're
Please.
talking about rubidium and barium ions actually. So are they
Yes.
salts like rubidium chloride and barium chloride?
No. So the source is that the source is from them, but again we'll have to have pure isotope. There are specific isotope within barium that we need to for quantum computing purposes. Not all isotopes are good enough, so we will have to have specific isotope of barium. It's a pure barium ion. So same is the case with the rubidium. It is not a molecule that we use. We use atom. You need to have a separate atom. So that is where you kind of that is where the whole technology is about. How from a rudimentary element of rubidium, which is available as a compound, how do you separate out the rubidium and then focus on playing around just with the rubidium?
Are these
So it is
available from BARC?
so very good point is some of them are available and some of them are available in the marketplace. Some of them are specific countries have a huge reserves of them. Incidentally, for India, we are one of the biggest sources of barium. So recently, when I met Honorable CM of Andhra Pradesh, Sri Chandrababu Naidu Garu, that's a point I discussed as well. There's a Mangampeta barite reserves in Andhra, which holds a 28% of global reserves of barium, and which is and QRAS of the world, and TriQuanta is born in barium. So all these systems will be based on barium quantum, and hence, though it is not a rare earth material, if you in the periodic table, it is in just one column away from that. It has many properties which is of significant importance. So to answer your question, there are different places where these are sourced from, including bark.
Thank you.
So that is where it is. And this is, I'm just sharing some of the samples. This is a schematic of how the overall system looks. But the point is that you will have the entire thing put together, and then there are so many components where mechanical, optomechanical, electrical, world has to get into place, and then eventually computer science will get quality qubits on which they can use a problem. They can solve some problems. So the point is that uh, mechanical engineering proudly is a significant enabler of quantum computing. These are some of the diagrams that I'm sharing. This simulation is done by one of the student of JNTU, final year student, where the vacuum stress is kind of analyzed by him as a part of the initial. This is very old project that we have given, but the point I'm trying to say is that students are actively getting involved in these projects, and that's how we build the capability and the future talent pool to create that ultra high vacuum system. This is on turbo. There is no ion pump involved, with baking. With the baking and the turbo, you can see that it is achieved to have 5.04 into the 10 to the power of -7 torr, which is achieved in some of our test chambers. So that is where we are, and where we are building the utilizing the neutral atoms scalability, trapped ions, fidelity means long coherence times, which enables high quality gates to be used. We are combining them to form a phenomenally powerful quantum computer, and the path to build our path is to build a logical. Today we are in a proto qubit stage because there are so many subsystems to be stabilized to achieve those qubits. We are very close to having working qubits very shortly. That said, very soon, hopefully, we'll be able to share good news about building qubits out there. So I would want to conclude saying that as you can see, as to the title mentions of for the session, there is phenomenal amount of opportunities that hybrid quantum computing opens up, and mechanical engineering has a lot of play in enabling this system. However, it comes with the challenges. You don't, unfortunately, as we speak, there are no ultra high vacuum making companies in India, and which means that's a challenge, but at the same time, it's an opportunity. Tomorrow's mechanical engineering students from Sreenidhi or all from the colleges of the faculty who are participating in this institute, tomorrow they might be the future entrepreneurs who will create these vacuum, ultra high vacuum systems right in India. It is not. It is somewhat easy to create turbo, rotary and turbo pumps, but to make ion pumps and deliver ultra high vacuum systems is not an easy thing, and we need a lot of talent to put their minds and solve these problems. So is the case with the materials requirement for quantum computing. While it is a challenge, there's a require that also means every challenge is an opportunity for us to solve, and that will significantly help in enabling the quantum computing going forward. So though originally planned for 45 minutes, probably I have went beyond little longer time. But that said, opening the floor for questions. At the same time, I'm sharing the QR code to connect with me anytime, and happy to be interacting over WhatsApp at mutual convenient times to further if you have any questions. But that said, opening the floor for questions, please.
Okay, participant. Now time for the questions. If you have any questions, please feel to ask. So before that, I want to ask you this question. Uh, the classical computer is basically the chip integrated circuit. So it's manufactured by, so many complex machines and all that. Like one is atomic atom layer deposition. That's one of the process. That means layer by layer, just one atom, like that, billions of transistors are built into the chip actually, as of today. As you said, the Moore's law, it has really predicted until this point of time. But I'm glad to hear that now it's not able to satisfy. At the right time, this quantum computing system is going to emerge because as that has reached its limit. Actually. So whenever I was showing this Moore's law, I was telling that it still is working, but now we should say that it reached its limit and then the quantum computer totally a different ball game taking over. But I have a feeling one thing, sir. In India, of course, what you say 100% accept it. That we most of us use the imported vacuum pumps for example, vacuum arc melting or vacuum induction melting, or the scanning electron microscope, transmission electron microscope. All these systems use very high vacuum. Can't say exactly 10 raised to minus 11 torr, but very high vacuum. So, but because those imported systems they are working good, it's a small scale. But in your case, it has to be very robust technology. But people in private also, there are companies which are struggling hard to maintain with the diffusion pump or ion pumps to give this. Many times there will be calls from the customers. Oh, again, it's not able to supply maintain the thing. Those problems are there. But that kind of technical know-how and struggles are known actually. So now it's a time to, work very hard and go towards it. I think this is the greatest opportunity. Person like you, I think, is going to keep India on top of the world. Uh, Congratulations. Thank you very much.
Sir, sir, excuse me, sir.
Any
Yes.
questions, please?
Yes, sir. Sir, I just want to know, like, what is the procedure to have access to the resources which are there in Andhra Pradesh, being in Hyderabad? Because whatever you said, it's fabulous, sir. Our students are very much interested to make use of them. But the only thing is, we do not have access to them. So, could you please help us in accessing those resources so that they can start working and gain hands-on and real-world exposure towards it?
Excellent question. Maybe I think we should connect after the session, and there are certain ways and means in which you can get in touch with the AP government, but not only AP government. NQM has a National Quantum Mission has a set of resources in I believe NPTL is the portal, I believe, but there are set of resources. But however, that said, there are certain ways to access these courses and getting acquainted with. You can drop me a note later, and then we can have a discussion on that.
Okay, sir.
Good morning, sir.
That's really good, sir. But is there any interns that we can apply for?
Yeah, so that is one thing that from quantum industry is just budding. So all our team members, all the startup industries, we are trying to meet up together and to create a portal wherein we will post requirements for internships, and academia will be also able to position the available candidates there, and the quantum computing startups also will be able to pick and choose from them. So this is something that is in discussion with that I've initiated with some of my colleagues across the quantum computing startups and players. So hopefully sooner or later we'll make an announcement and share it with you. You can follow our social media handles and as well as me, and hopefully we'll make an announcement wherein your interns can get an experience. So for example, I showed you a diagram of vacuum chamber that is done by one Mr. Varun. He's a third year completed student in JNT College of Engineering. He did the completely by himself. So to answer your question, there are
Yes, sir.
opportunities.
Great, sir. Great words from you, sir.
Yeah.
Sir, this is
So
Dr.
please,
Balraj.
can we have your contact details, sir, so that we can reach you?
Yeah, I have I'm sharing it on the screen already. I don't know if you can see.
Thank you very much, sir.
Sir, this is Dr. Balraj, SNIST. It's very nice presentation, sir. It's a wonderful presentation in this new area of quantum mechanism. Hello, sir. My voice is audible, sir.
Yeah, I can hear you. I can hear you, sir.
Sir, thank you very much. And really good news to see. I heard about the development of Andhra Pradesh in the area of the quantum. So good, sir. And I think one more important thing is the awareness of the students is also very less, sir, in this area. So if possible, why not you include it in the syllabus of the mechanical engineering? Because the bright future in this area in the future. So I request this is take initiation to the people of mechanical final year or third year and give the internships also in this area, especially for the SNS students. It is
That's a
good to us
great.
also.
Thank you very much for your kind words, sir. And yes, in fact, that is a thought process, and I have requested as I said, I was part of BOS team, BOS body for R25. And for about 3 days, we worked on various modalities and ensured that there's a topic carved out. So the way we structured is that we need to have, because we have R&AC any which ways in the curriculum, why not extend it a little bit and to make sure a placeholder for cryogenics and specifically quantum computing enabled cryogenics, so that that will start them there. And then you have a full-fledged minor, say in the final year, to have this. So that was the thought process. Those were the things, the recommendations that were given in R25. And to the best of my knowledge, I think they are included already, if I'm not wrong. And the vision is that, sir. The idea is that this has to be that was a dictat, Honorable Vice Chancellor T.K. Reddy Garu, who is my mentor as well as head of the department when I studied mechanical engineering. So he has guided us in the BOS as well to include industry relevant topics in BOS. And this is already there, if I'm not wrong, in R25.
Thank you, sir. Thank you.
Sir, just one question, sir.
Sure,
This
please.
ISRO, Indian Space Research Organization, some few years ago, they were asking for the manufacturing the outer orbit. I mean, that means very, very nanoscale, that kind of things, okay? So I think the quantum computing, it will find it outer orbit as a home, actually, because vacuum issues will not be very troublesome. That kind of thing. What is your line of thinking on that?
I think that is a brilliant point. In fact, very, very, very insightful one. So eventually, you must you be following, right? To utilize the specifics in outer orbits, data centers are being planned there. Already, some startups have started working there and moving the AI data processing to outer orbit. So I think this is naturally right. I mean, come to think of it, in outer orbit, you don't have as much as struggles as on Earth surface with respect to vacuum, ultra high vacuum. So I think eventually possibly that's a brilliant suggestion. So maybe I can take your inputs further on possibly how to develop it further and can work and collaborate on that front. Very happy to listen that suggestion. I'm thoroughly in appreciation for that. Thank you very much, sir, for your kind words. And I thank Indira Rani ma'am formally on the record for providing me an opportunity to connect with you. And she has been a guide, inspiration guide for not just for me, for many of us to take up challenging works, and they continue to inspire, including our Honorable VC T.K. Reddy Garu, who continue to set new challenges to us. So that said, I am hugely indebted to my alumna, alma mater, JNT College of Engineering. And as you rightly said, Srinivasul Garu, we have phenomenal role. Believe it to me, next generation of quantum computing is enabled by students whom you are going to touch now onwards and inspire them to take up creating systems. Incidentally, if you can solve for ultra high vacuum or precision engineering to the kind, if you can solve it for quantum computing, then you are all automatically solving for many other industries across pharma or space or so many areas get automatically solved in the process of creating for this. So I thank you for giving this opportunity to speak in front of such an eminent panel of experts.
Dr. Purushottam sir, Dr. Patel sir, if you are online, please, you may ask questions.
Good afternoon, sir.
Hello, ma'am. Please tell me.
Sir, actually, in the last slide, you have talking about that quality gates to produce the qubits,
Correct.
process the qubits, I think.
Correct.
What is meant by quality gates, sir, and what parameter we can say? Generally, you spoke about the Hadamard gate, poly gates. And how can you say quality gates to process the bits?
Wonderful. A brilliant question, ma'am. Actually, what I'm referring to, my view of perspective of that is that, so these gates need to be stable. So as you can see here, you are playing around with atoms and ions in an extremely specialized zones. So you have to maintain ultra high vacuum, etc. But if there is any thermal vibrations or physical vibrations of any sorts, etc., these are going to interrupt with the coherence states. The moment the coherent states get impacted, the gates get impacted. And the quality of gates means how long you have high fidelity of these gates is what I'm trying to mention. It's about having stabler, it's about the stability aspect that I'm trying to tell when I meant about quality gates.
Okay, sir. Thank you, sir. Thank you.
So in fact, if possible, I'm trying to showcase some of the hardware that we have already met, but possibly after the session I can share because all of them are in lab. So to make that cathode, one of the areas is about materials, right? How do you? So we need a specific dielectric materials to ensure perfect isolation and specific parameters to make the ion traps. So in each of these areas, a lot of mechanical engineering design, simulation, manufacturing using precision engineering is required. And hence, if we collectively across this table can inspire next generation of engineering students to go to the simulation tools that universities are already providing and make best use, because by the end of them they are outside of the campus, they should be able to take a system, take a drawing, and then be able to kind of completely do a simulation of ultra high vacuum or electromagnetic simulations. They should be ready with that knowledge. So collectively, if we can enable it, we are doing a great service to the nation. So before conclusion, may I request Srinivas Garu, if is it possible for everyone to come for a brief moment for on camera so that we can take a group picture, which I which we can possibly share in social media, and this will inspire many future mechanical engineering aspirants to take up quantum computing seriously. So back in physical meetings, right? That's a great opportunity, but in online, this is the only way. So the point is, once we take a group picture and share in social media, that will help inspire many other people further. Maybe after the call, I will share some of the books that can help the participants to, over a read, casual reads, they'll be able to gain knowledge in quantum computing. Maybe Srinivas Garu, since you're the host, you can take a picture and
తీసుకున్నారా?
Indira ma'am, thank you very much.
Good morning, Chaitanya. Thank you. Thank you for a very excellent session. I have shared to my students also, and even I think Dr. Ravi was also there. It was a nice session listening to you. But this was, I was expecting that we wanted to arrange in our department. But anyhow, this is the second session I have attended of yours. Really very good information. I wish you all the best, Chaitanya.
Thank you very much, ma'am.
Sreenidhi Reddy, thank you very much.
Thank you, madam, very much
Thank you,
for
sir.
arranging this lecture for us. Thank you.
Thank you, sir. Thank you.
Thank you very much, Sreenidhi team, for opportunity. Thank you, ma'am, again. Thank you, participants, for sparing your valuable time.
Thank you.
Thank you, sir. Thank you very much.